So, I'm very excited to be here after all the setbacks that I had on the way. But as I said, today I'm going to talk about word generative models that actually understand the visual world. And I'm going to skip this introduction because you gave such a nice introduction of me, I couldn't do it better myself. So let's talk a bit about the motivation, okay? So, deep learning and neural networks have existed for a long time. But in the 2020s or around 2010, they started to get really good. So this is some of the things that we can do around 2026. You can see here Flax2 by Black Forest Labs, of course, Sora by OpenAI, and ChatGPT by OpenAI. So all of these are advancements that happened in the last maybe 20 years, but weren't possible before. So we all know that the secret sauce and the thing that companies rely on very heavily is, of course, scaling, right? The ability to scale the model, the ability to scale the data, the ability to really use the massive resources that we have currently. So the 2010s, as ELLIS said, and this is a citation that I really like to use, were the age of scaling. We took models, we made them larger, we took data, we made it larger, more generic, less inductive biases, and we got all these amazing models. Now the question is scaling enough? Or is this entire field of deep learning just summarized and boils down to more data and more scale? There is a finite amount of data that we have, right? And a finite amount currently that our GPUs can support in terms of scale. So if you remember, the first iterations of deep learning models or deep foundational models that we released were huge leaps compared to one another. But right now we're starting to see some type of plateau where data and scale is not enough. So thankfully for us in academia, we're back to the age of wonder and discovery again. So we're taking a step back from scaling and thinking also algorithmically. How can we improve the models themselves, the architectures themselves, the training mechanisms themselves, to not just rely on scaling? And I think the best example for this is probably video models, where we've worked on video models for a really long time now. This is an example from VO3. Okay, so VO3 developed by Google. For all intents and purposes, a company that doesn't lack resources, doesn't lack data, doesn't lack scale. But it seems like there is some barrier that we can't cross with the amount of data and scale that we have currently. So we can't really get models to really faithfully understand the world that's surrounding them. So physics is a great example, right? Motion is a great example, but also very basic stuff. Like counting, this is Opus 4.7, and he actually updated the slide the last time I gave this talk, and it was the day that I gave the talk that I added this. It is confirmed we reached AGI. How many P's are in strawberry? There are 2 P's in strawberry. It's not what I wrote, but okay. And just to note, the correct spelling is strawberry, not strawberry. So A, error in counting. B, error in actually copying just the word that the user used, right? So this is even in LLMs, where LLMs are considered right now, general population information for the mass crowded, right? Not just us in academia, in the industry. So models seem to get it wrong in very, very basic ways that we as humans feel are trivial, right? So we're not there yet, and it looks like data and scaling for now is not really solving these issues. I'm going to give a brief overview of the research that I did. Okay, it's very hard to summarize 5 or 6 years of research in 2 minutes, but I'll do my best. And then we'll dive into the actual work that we're going to talk about today. But today we're going to talk about how do we understand why models still have malfunctions, and how can we fix that systematically, okay? So I started my way around 2020. I did a lot of classic attribution map works. These are 2 works from CVPR and ICCV that took basically classification models. This on the bottom here is CLIP, and on the top here is the VIT. And what they did is actually created an attribution map over the input. So basically, if we see here a teddy bear, the model predicts that this is a golf ball. An attribution map gives us a heat map over the input, which indicates that the model looked at the paw of the teddy bear and inferred by just the paw that this is a golf ball. Okay, so explanations that can give us some insight as to how the model did what it did. From 2022 on, and I believe that some of the works that I'm doing right now still fall under this category, I work on what is now called actionable interpretability. In 2022, especially in vision, I don't think anyone was really familiar with this term, But actionable interpretability means how can we take this observation that we had here and actually make this an actionable signal? How can we use those interpretations to actually fix the model? So what you're seeing here is a work that we did for NeurIPS, where we actually fine-tuned the explanation itself. So the explanation, because it's based on gradients, everything is derivable, and then we can just ask the model to optimize the explanation rather than optimize the actual classification. And what we found is when we optimize the explanation to just be on the entire foreground, the model is able to self-correct or fix its own prediction. So it's not that the model doesn't know what a teddy bear is, it just wasn't looking at the right areas, okay? So I did this for both classification models and generative models. And today we're going to talk about my latest line of works, which is the foundational line of work. Okay, how do we actually fix models? How do we actually build models that understand or don't have those limitations that we saw in the beginning? So I'm going to present a couple of works today. The first one is called Attend and Excite from 2023. And there is going to be a theme to all these works. And the theme is, why isn't this working? Okay? Because I work with models a lot, I try a lot of different things, and when I try something like a cat and a dog, and in 50 to 60% of the cases, with amazing models, really at the time Stable Diffusion 1.4 was the best, the state of the art, in 50% I got either 2 cats or 2 dogs or weird mushes of cats and dogs to this single object, okay? So this entire line of work was inspired by my work on interpretability. How can we take this to the generative realm and ask why isn't this working? So let's try to understand what happens here. And in order to understand that, we're going to try to understand how this model works. This model is a diffusion model. And what a diffusion model does is it learns to gradually denoise. It takes a pure noise signal, x1, and gradually removes noise from it. Because creating pure signal from pure noise is really hard, right? So we break this process down. We first do the coarse tasks, like the structure and the layout, and we add information as we go along with the denoising process. So let's understand how this model is actually conditioned on text, okay? Because I want to give a text prompt like a cat and a dog, and the model needs to be conditioned on the text prompt. So here is the diffusion process, what you're seeing here. We have this single diffusion step from zt to zt minus 1. And here the conditioning text is a lion with a crown, okay? And inside that diffusion model, where we do the actual denoising, you can see that the model is conditioned on the text via these orange layers called cross-attention. So cross-attention is where information is transferred from the text to the image, okay? This is how the model is conditioned on text. And then the first observation that we can make is if we want to understand why the model generates just a lion and not a crown in this image, maybe we should look at the cross-attention connections, right? Because this is the only entry point that text has into the image model. So let's take a look at cross-attention and how this works. So cross-attention is a bit more complicated than what I'm going to show you now, but for the purposes of this discussion, we just need the queries and the keys. So the queries are a projection of each one of the patches in the image. We take our noisy latent ZT, we split it into even-sized patches, and each query represents a patch in the image. Okay, so we have a vector representing each one of the patches. And also for the text tokens, we have a vector representing each token in the text. And then what cross-attention does is it creates this similarity matrix or attention relevance matrix where each row corresponds to a patch. So the first row corresponds to the first patch, the second row corresponds to the second patch, and so on. And what we do is we create a distribution over the text tokens for each patch. So basically this distribution means in terms of relevancy or in terms of explainability, okay? How much information or how much relevance does the word a has to the first patch? How much relevance does the word lion has to the first patch? And so on and so forth. And for each row, we create a distribution over all the tokens, right? How much is each token in the text important or relevant to the first patch? Any questions on this? Okay. So now, instead of looking at the rows, we can look at the columns. Each column represents a text token, right? And then we have activations for that text token across all the patches. So we know how much each text token impacts each one of the patches in the image. So we can take those columns and reshape them to visualize a heat map over the entire patches in the image. And what you're seeing here is exactly this reshaping of each one of the columns. So we can see that the word gets no relevance for any patch in the image. Basically, no patch in the image is similar to the word a. We can also see that lion gets very high activations around the region where the lion ends up being generated in the final image, right? So this is a good indication of where the model looks or what the model looks at to actually generate the output. What we're seeing here is kind of, you can see the structure, but these attention maps are a great indication even when you have pure noise. Even in the very first steps of the generation, you can already see in the cross-attention maps where each object is going to be generated. Now, one observation that we can get at is that lion has high activations in some patches in the image, but crown has no high activations anywhere in the image, okay? And this is the observation tool that we can use now to understand this problem. Why is crown not generated and lion is generated? No attention. Low attention equals no generation. Simple as that. When cross-attention transfers information from the text to the image, if I completely ignore crown, the model has no way of getting any information on crown anywhere else in the process, right? The cross-attention is the only place where text meets image. Is this clear? Do we have any questions on this? Okay, so we have this observational tool now, right? This is exactly the attribution maps or the heat maps that we talked about before. But I said that this is an actionable interpretability work, so we don't just want to interpret, we actually want to fix based on the interpretation. So how can we use this observation to fix the model? Well, let's just create a loss term that translates our intuition into math, right? We said that lion is generated because it has a high maximal activation. Somewhere, some patch in this image decided that lion is important. Crown is not generated because none of the patches in the image decided that crown is important. Let's translate this intuition directly into a loss function or an objective function. So the objective function is the complementary of the maximal activation. And then for lion, this loss function is going to be very low, right? Because we have high activations. For crown, this loss function is going to be very high because none of the patches think crown is relevant to them. So this is the loss, right? This is the loss that we're optimizing, the maximum over all the nouns in the sentence. So let's take the maximum over L2 and L5 and just do a gradient descent step. So we're optimizing ZT, we're optimizing the latent such that the most neglected token crown gets attention somewhere in the image, okay? This is just a translation of what we observed from the heat maps to a loss term. Now, why are we optimizing ZT? Because if you remember, the queries were a projection of ZT, of the image. So when we're shifting ZT, we're basically shifting the queries and asking them, please attend to this token that is neglected. Where? Anywhere, right? The model can choose where to place this new token and where to place this attention, because what I demanded is just that there is some patch in the image that has high activation, which is nice, and you'll see why this property is important later on. But this is a very loose objective. So what we now do is we have this single denoising step that we talked about from ZT to ZT minus 1 at the top over there. We're going to look at the cross-attention maps for each one of these steps, right? We're going to apply the loss, shift ZT, and repeat the same diffusion step again, but with the shifted ZT that is encouraged to look at everything. And you can see the result with a tendon excite and without a tendon excite, where with a tendon excite, the lion is actually generated with the crown, okay? Now, why is this cool or why is this interesting? As I said, these cross-attention maps are nice and visible even when the image is very noisy. So you can see that throughout this optimization process, we can entirely change the layout of the image. It's not like we're artificially adding a crown on top of the lion where there's no real room in this image, right? The model can change the entire layout because we're operating on the core steps of the diffusion process. Yes, so the entire layout of the image can and does change. And we can apply this optimization even when the image is super noisy and we don't have any signal in ZT yet. Any questions on this?
Am I only checking for the nouns, not for the other words?
That's a perfect question. That's a really great question, because it doesn't work for other parts of speech. This entire analysis is based on the fact that the attention maps show high activations when something is generated. Something that we can't do if the attention doesn't grasp something, and it doesn't grasp a lot of things, like counting, it just doesn't show this. Or relations, it just doesn't show this. It's not sensitive to it. So attend and excite is really a tool at inference time. If the model can do something, we drive it to do something. So for example, if a prompt succeeded in 0% of the cases, it means that the model just can't do it. This is an inference time fix, right, to a training time problem. So this can only fix what is in distribution. This is nice, but again, like I'm going to get to self-flow at the end of the talk, which questions how do we fix this systematically? How do we fix this in the pre-training process? Oh, we had another, yeah.
One more question, how do they differ through the diffusion process? So do the attention maps look different, like when it's very noisy compared to when it's nearly generated? Like how do they shift over time?
That's a great question. That's a great question. I haven't noticed any, extreme differences between the cross-attention maps in the noisier parts and the less noisy parts. What's important for this is that we have to change the layout of the image. We have to be able to have this tool to change the layout of the image. When you apply attend and excite in later steps, what you're changing is mostly high frequencies. And then what you'll see is mostly artifacts. This is why this is cool, because it doesn't require us having any prior knowledge on what the image is going to look like. It basically gives you a cue before you've done any denoising or done very slight denoising.
Are you having negations in this setup?
So negations, you can just take this objective that we have here with the 1 minus and just flip it, right? If you want an object to get no attention, your objective would be that the maximum is still 0. So negations is actually something that we can handle, but other parts of speech is something that is unmanageable under this process. And also exposes to us that the model doesn't really learn, or at least doesn't learn in the cross-attention maps, a bias on counting or on relations, which hypothetically we would want it to have. Okay, so let's take a look at examples with attend and excite. So before and after, and as I said, the model can choose to completely change the layout of the image to fit what we want. And this is actually a cool property in my view, because you're not really forcing the model to generate anything in any particular area. So any subject can be generated anywhere in the image, and this is where the model uses its prior, right? If I want a cat and a dog, the model knows what the layout of a cat and a dog looks like. This is actually one of my favorite samples, which shows why a non-restrictive objective is great. Because here I want a playful kitten chasing a butterfly in a wildflower meadow. And then it's not just about generating 2 subjects, right? A kitten and a butterfly. The kitten needs to be chasing the butterfly. So the model needs to use its prior to understand not just how to place both objects in the image, but how to place them in a way that fits my prompt. And since my objective is non-restrictive, right? It's very loose. You can place any object wherever you want in the image. The model uses its prior knowledge to place both objects in a way that fits my prompt. Okay? This is why I personally usually shy away from methods like, here is a specific region. I want you to put the butterfly specifically in this region, because then it limits the model's ability to use its prior knowledge to fit the scene to the prompt. Okay, so let's summarize attend and excite. And this is, by the way, short on purpose, because we're getting at a point here. We're getting at a point of how can we improve the model during pre-training and not as a post-hoc side thought. But with attend and excite, without attend and excite, we couldn't do conjunctions. We had no prompt alignment. With attend and excite, we can generate conjunctions which fit the prompt, right? Which are prompt aligned. We did this without training and without additional data. And this is a point on, this is a post-hoc fix and not a foundational fix on how can we train models that actually understand this. Another work that I'm going to show you along the same lines is Video Jam, which I did at Meta AI. And video generation is a very, very, very research topic in the last year in particular. And I think we got to some pretty impressive results. But as I said, physics, motion, the ability to understand really simple things, like if I bang my head on this table, my hand can't just pass through the table, right? It's not something that we were able to fix from just data and scale until this point. So the question was in VideoJam, why is this? Why does this happen? And we hypothesized that the model is not very sensitive to temporal information. And how did we confirm this hypothesis? We took a model. This model was trained on regular videos like the one you see here. And we randomly shuffled the frames. Okay, if the claim is that the model is not sensitive to temporal information, this, if you look at this frame by frame, it looks okay. If you look at the entire video together, it looks scrambled, okay? So the claim was that the model is not good at distinguishing between these types of videos and these type of videos. And what we saw was that when we took both these videos and noised them and calculated the diffusion loss, I would expect that the loss of a trained model on a scrambled video would be much higher, right? Because it's not temporally coherent. So the model predicts something that is coherent, compares it to something that is incoherent, loss is high, right? Model computes something coherent. When we compare it to something coherent, the loss will be low. But we couldn't find any. These two orange lines are the DIT, where we fed them videos that are regular and scrambled videos. We couldn't really find a statistically significant difference between videos that were scrambled and videos that were unscrambled. In essence, when you feed to the model a scrambled video and noise it, it can't distinguish between that and a clean video and be like, okay, this is a good video, this is a bad video. So essentially our objective, our denoising objective for a diffusion model is not very sensitive to temporal information. What you're seeing in blue is after VideoJam, okay? So what did we do in VideoJam? What we did is we added an explicit temporal prior, okay? So instead of just teaching the model to denoise RGB information, we taught the model to denoise simultaneously both RGB and optical flow maps represented as RGB. So what is optical flow? Optical flow, for those of you who don't know it, it's an old school computer vision representation, a problem that is considered already solved. And what optical flow does is it estimates trajectories, right? Direction and intensity of movement between pairs of pixels. So what you're seeing here, each color represents a direction. For example, purple is forward to the right, green could be backwards to the left, and so on and so forth. White means no motion, so we can see that the background has no motion in this case. And the intensity of the color indicates the intensity of the movement. So basically what we're teaching the model to do here is not just denoise the visuals, not just the RGB information, but denoise the visuals and also a motion-specific representation jointly. To denoise this, we need to understand the direction in which each patch is moving, right? Because the colors here don't indicate RGB information, they indicate motion. And this worked pretty nicely. Nice to the extent that with VideoJam, with I think it was 300,000 videos that I fine-tuned on, we were able to outperform at the time Sora that was the state of the art. And we were pretty surprised by it because we had significantly less data. So this is another indication of, okay, maybe it's just not the data and not just the scale, but how do we apply it? How do we take the data and the scale and actually encourage the model to learn something meaningful from it? How do we create an objective that is hard enough for the model to actually learn something meaningful from? So, what I wanted to point out about both Attend and Excite and VideoJam, that they are post hoc solutions to specific issues, right? So, in VideoJam, we used an explicit motion prior with optical flow. With Attend and Excite, we also used an explicit prior or an explicit bias with the semantic maps, right, the heat maps, that indicated whether an object exists or not. But in both cases, we took a specific problem and we proposed a specific solution to that specific problem under the assumption that the model just can't or isn't able to learn this from the data. So what happens when we want to train an omni model, as all the labs are now trying to do? We want a single model to understand all these things. We want it to understand conjunctions, and we want it to understand motion. and we wanted to understand physics. And how can we even encode physics in an explicit prior that we teach the model with? So it seems like it's quite unfeasible, as we said, for example, in the attend and excite case, right? When it's not conjunctions, but counting or colors, it's not feasible to just continue to find post-hoc solutions to problems that exist in the pre-training of the model. Then we probably need to fix the pre-training process of the model, which is the idea behind self-flow, which is the work that I'm going to talk to you most about today. This is our latest work from Black Forest Labs. So the idea was, okay, let's take a step back, and instead of diagnosing or analyzing each problem separately, let's try to understand the common denominator. What is common to all these problems? And in the center of self-flow, there is a hypothesis that the center of all these problems is a localization bias. Okay, now I'm going to explain the hypothesis. You can choose in the end of the lecture if you believe this hypothesis or not. But if you don't believe it and want to disprove it, I would be very excited to read your paper. So what we do in diffusion models, and usually when we train generative models, is we calculate this MSC loss. And this MSC loss, what it does is it looks patch by patch, pixel by pixel, however you want to quantize your data, okay? And it compares the patch verbatim. So we have our original image and our generated image, and we just compare each patch between the original image and the generated image. Now, if I want to reconstruct or recreate the nose of the cat, which patches are most important for the nose of the cat? Is this patch over here important, or which? Usually the localized patches, okay? So whenever I want to reconstruct, say, I don't know, this is the nose of the cat, okay? And this is a very distinct patch that has just background information. The model is more likely to look at the neighbors, right, to do this reconstruction process. And what we claim is that this creates a localization bias where each patch is mostly dependent on its neighbors, and the model is less incentivized to look at globalized connections across patches. What's one support of this in the examples that we saw before? The two mushed dogs example is a good example of a localization bias. Because if you take each one of these patches separately, it makes a lot of sense that this would be a patch in an image of a dog and a cat. But overall, the globalized representations are off, okay? Same for the motion problems with VideoGem. You take each spatiotemporal patch, it looks okay. Globally, as a cluster of patches, it doesn't look right, okay? So the hypothesis is that the model is focusing on localized information and failing to create globalized representations that will give it the robustness that it needs. Any questions on this? Okay. So there is an entirely different field of research called representation learning. It's been interesting to a lot of people. Maybe you've heard of it. And I chose to give here maybe the most abstract definition from the seminal paper, Representation Learning, a Review in New Perspectives. And this definition is learning representations of the data that make it easier to extract useful information. So basically, representation learning can be anything. But the way that I think about representation learning versus generative modeling is basically summarized in this slide. So generative modeling, high frequencies are super important. We want to create images that look real, high resolution. This is super important to us. This is what we're optimizing on. In representation learning, we don't really care. We want to create this overall globalized, very loose, very uncommitted representation of the information. So this is a representation learning case for a cat versus what we would expect a generative model to do for a cat. So you can see why localization versus globalization is different for each one of these tasks. This task has to be localized. It has to understand localized information in order to create high frequencies. This task doesn't care about high frequencies. It doesn't need to generate anything, so it creates abstract globalized information. Question on this? Okay. So now we have this new hypothesis. Maybe if we have good global semantic representations, we wouldn't need those manual external priors that we had with Attend and Excite and with VideoGem, because those globalized representations will be strong and robust enough to encapsulate physics, encapsulate motion, encapsulate conjunctions, okay? Maybe. We don't know, but maybe. So we weren't the first ones to think that it's a good idea to combine representation learning with generative modeling. Maybe you've heard about this paper. It's called REPA, representation alignment. And what this does is it takes our generative model, the diffusion model that we talked about before, and it takes an intermediate layer and aligns it with a completely unrelated encoder. So this encoder, not trained in the same setup, doesn't know how to generate anything. It's not a generative model by any means. It was trained to be a good representation learner. And we aligned those two models. And there is something to me very unintuitive about this thing, because this model needs to understand high frequencies. This model does not care about high frequencies. This model was trained with noise. This model was trained only on clean information. Oftentimes, these models were not trained on the same data with the same distribution at all. So why would we even align these two models and expect something nice to happen? Well, it turns out that not only does something nice happen, something really, really, really nice happens. You can see here the training process across the training steps of a DIT model to generate on ImageNet classes. And you can see in the top row some of what we talked about with the localization bias. So again, each one of these patches looks okay, but if you combine them overall, global properties like structure are just messed up. And you can see on the bottom what happens when you add REPA to the mix. So what REPA does more than anything, I think we can see it here, is it fixes globalized structure, right? The image doesn't look as scrambled as it did before. So we can ask ourselves, what would happen, oops, okay, no worries, I don't have that slide. But what would happen if we train for a long, long, long time with REPA versus what would happen if we train for a long, long, long time without REPA? So we see that even if we train for a long time, this is maybe our DIT model, and with REPA, we can see that even the convergence point after 7 million steps is much better. So it's not just the fact that we're using or bootstrapping from an existing model. Even when we look at just training to the extreme on this, and this is on ImageNet, so just 1.2 million samples, right? This is not a huge data. Training it on 7 million steps is a long, long, long time. You're already way, way, way beyond the saturation point. And this is REPA. So REPA seems to be helpful even when we train to the extreme. Okay? So where's the catch with REPA? The catch with REPA is what I call the Dino V2B paradox. If you look at all these papers, they start from Dino V2B. RAEs as well to Dino V2B. And in CellFlow, we did this very basic experiment of what happens when we take a model that is stronger than Dino V2B, a better representation learner. What happens when we increase the model size or go from V2 to V3, which was trained on more data and is more generic. And what turns out is that this actually gets worse. So scaling laws, which is what we began with, right? Scaling laws is what makes this entire field actually work in practice. They don't really work when we do representation alignment, okay? So we can throw scaling laws out the window. Dino V2B is always the best model to align with, which is sad, really, because we would want, ideally, as we scale the model, to use a better representation learner as well. Any questions on this? Okay. So now that we have this scaling law paradox, we can also understand why this happens intuitively. The reason this happens intuitively is that we, again, have two models that have nothing in common, and we're trying to align them both. They are not speaking the same language. They have not trained for the same purpose. Dino V2B is not a generative model. So of course, we can't just scale it and expect the same scaling laws to apply. Then the idea behind CellFlow is, can we get the best of both worlds? Can we train a generative model to also be a representation learner in the pre-training process? Not in post-hoc, not as an afterthought, but actually create a pre-training framework that does both of them at the same time. So generative modeling and representation learning at the same time. What we're seeing here is the infamous localized cat example throughout the diffusion denoising steps, from pure noise to pure signal. And now we can think about a natural candidate from the representation learning world. How can we turn this diffusion model into a representation learner? masked autoencoding is maybe the most natural candidate. And the reason for that is that masked autoencoding also takes into consideration some hidden information. And we can consider this noise to be the hidden information or the platform to hide information. So what usually we have in masked autoencoding is we have this partial observation where we take some random patches in the image and completely black them out. Okay, so the model can't look at them at all. They don't exist. We either completely take out those tokens from the sequence or completely black them out, which we can do by noise, right, in the denoising process. And then we have a student model, or sorry, the teacher model sees the complete data, the student model sees the partial observation, and the objective of the student is to match the teacher's representations without seeing the full information. Now, why does this prevent localized information? Because if I want to denoise this patch here, I have to look at globalized connections because its neighbors are all super noisy, right? So this explicitly forces the model to create globalized connections, which we hypothesize it doesn't with just the denoising objective. Okay? Is this point clear on why we want to use masked autoencoding? Okay, so what's the most intuitive and naive way we can incorporate masked autoencoding into the generation process? We just take a random number of patches and completely noise them, right? This is kind of the natural equivalent of masked autoencoding. And this would theoretically prevent our model from using localized information because, as we said, the localized information is often completely noisy, so it has to look at globalized connections to actually do the noising task. Okay? Questions on this? Okay. So, when you do this very naive masked autoencoding thing, the performance actually gets much worse. So we have here in blue the vanilla model, the vanilla DIT model, here it's SIT. And in orange is the version that we talked about with the masked autoencoding where we randomly mask patches in each denoising step. And can anyone hypothesize why this is happening? I'll just give the answer. So the model still needs to function as a generative model, right? It needs to create those high frequencies that we like so much. But here, at each step, we're kind of preventing it from learning the high frequency information because at each step, we have a significant amount of noise. So the model struggles very much with understanding high frequencies. We never show to the model during training a case where you need to infer basically only the high frequencies. There's always low frequency information that the model has to infer because it always sees a heavy amount of noise. So we basically dumped out the window the biggest advantage that diffusion models had, which is they do gradual denoising, so they learn everything from coarse to fine. Okay? So there is a real problem here, a real tension between the generative objective, which needs high frequencies, and the reconstruction or representation objective that needs globalized coarse representations. So how do we solve this problem? How do we settle this tension between globalized and localized, between representation and generation? The intuition is exactly like what we had from GANs to diffusion. So in GANs, we did a single step to denoise. In diffusion, we said, no, noise doesn't have to be binary. It doesn't have to be completely noisy or completely clean. It can be anywhere in between. So why not do the same thing for masked autoencoding? Why does masked autoencoding need to be binary? Why is it always completely clean or completely noisy or completely hidden? We can do the same thing that we did for diffusion for this masked autoencoding process. So instead of being completely clean or completely noisy and shifting to completely clean, we can show the model all options in between. We call this dual time-step scheduling. So instead of drawing one time step from the distribution in the noising process, we draw two time steps, one of them being the noisier and one of them being the cleaner. These two time steps can be either very different from each other, simulating masked autoencoding, or very similar to each other, simulating diffusion, okay? So the idea here is that masked autoencoding, similar to noise in the diffusion process, doesn't need to be binary. It can be continuous. It can and should be flexible. Any questions on this intuition? Okay, so how do we apply it in practice? So as I said, we are applying it to a diffusion process. And during training, we have our pure noise and pure signal, and we choose an intermediate point T, okay? And then we mix the noise and the signal linearly. This is what we do in flow matching. So the key here to everything we're going to do from here on is this T, because this T determines how much noise we actually have incorporated in our signal, okay? Now, what we're going to do is instead of just choosing one T, one time step, we're going to choose two. And the two of them are going to be from the same distribution PT, which is the noise distribution, the regular noise distribution we use for the diffusion model, right? So different diffusion models can use different distributions. For example, if we want to train a video model, our noise distribution will emphasize more higher noises because we have a lot of redundancies. Okay, so we need a lot of noise to actually conceal information. If we have low-res data, this distribution will be more similar to uniform, but at the end of the day, what we do usually in a diffusion process is we draw T from PT, where this is the noise distribution. And here, instead of doing this, we're going to draw two time steps, T and S, both from PT, and they are sampled IID. So there is no relation between them. One can be very high, one can be very low, they can be the same, they can be any combination. And then during training, what we do is we noise some of the patches with one noise and some of the patches with another noise. We can create this entire range where the two time steps are either the same, which is what we did in vanilla diffusion, or the two time steps are very extreme. One of them is 0.2, so not a lot of noise, and the other is 1, which is more similar to masked autoencoding. So basically, during training, the model sees this entire range, and it needs to understand any continuous amount of two noises. Okay, this is what the model is now trained to do. Questions on this? Okay. So let's formalize this mathematically, because we have to. So for each patch in the image, we're going to draw 1 or 0, right? We're going to flip a coin. If it's 1, it's assigned T. If it's 0, it's assigned S. What this means is that we have another layer of randomness, because for each sample, the assignment of T and S changes across the patches. So it's not like the same patches are always assigned T and the same patches are always assigned S. And then we're going to noise each patch based on T or S based on the assignment that it has from the mask, okay? So some tokens are going to be noised with S, some tokens are going to be noised with T. Okay, now this masking ratio that we see here on the top, RM, also depends on the modality that we have. So for example, for video, you can imagine that since we have a lot of redundancies, this masking will only be effective if most of the patches are masked. If we do 50-50, and only 50% of the tokens are masked, what's going to happen is that even this masked autoencoding objective is going to be ineffective, because the model will be able to use redundancies to just infer the information from the neighboring patches and the neighboring frames. So this RM depends on the amount of redundancy that we have in our information. For video, we would want to create a high discrepancy. So for example, maybe say RM is 0.9, such that most tokens are noised with T and only a small minority with S. On the other hand, if we have images with a low resolution, we might want to use RM to be even 0.5. But this is important to set this according to the amount of redundancies that we have in our information. For this masked autoencoding to actually be effective for anything. Otherwise, this masked autoencoding is just useless. Okay, and then we're going to basically noise each patch with its corresponding noise. And during inference, we can still do the regular diffusion process because it's in distribution. The model did see cases where T and S are identical or almost identical, so in practice identical. So when we do this denoising process where the entire noise is uniform across all the patches, this is not out of distribution for the model. It did see it during training when T and S were close. Question on this? Okay. So very interestingly, despite the fact that we're creating this train-inference mismatch still, right? We talked about it in the naive masked autoencoding version, but this also exists with DTS, with dual time subscheduling, because at training we show two noise levels. At inference, the model has just a single unified noise level across all the tokens. And still you can see that DTS is the best of all these options. So even without, we talked about representation learning, right? We talked about the student needing to reconstruct the teacher's features. Here we didn't still add the self-supervised objective. We just changed how we schedule the noises during training. And even just doing this is giving us a nice boost in FID. This gives us a good idea that the model wants and yearns for a harder training task, okay? The training task of denoising with a uniform noise just seems too simple for a model to learn something complicated, a complicated representation from. And it looks like even though we created this train-inference mismatch, again, this training doesn't completely fit inference, it is actually helpful for the model. So let's look at the entire self-flow pipeline. What we talked about so far is just how to create this X tau, where we have two different noise levels to the image. But the entire framework is actually very similar to masked autoencoding with this asymmetry between the two noises. So we have our student that sees the mixed noise. We have the teacher that sees only the cleaner of the two time steps. And then the student is trying to do two things, both the generative objective, the regular generative objective, and the representation learning objective, where it should reconstruct the teacher's features from its partial information, okay? So the student now needs to use its partial clean patches to infer the representations for the missing noisier patches. Questions so far?
Is this this matching of the representations in the representation space, or directly exists?
It is in the representation space. And if you want to read a bit more about it, you can read in the JEPA paper. They were the first ones to kind of emphasize that it's very important to do this reconstruction in the feature space and not in the pixel space. Again, the objective of this is to actually do the opposite of pixel space operations, high frequencies, but focusing on coarse representations. So it is done in the inner layers. You take an inner layer from this model, an inner layer from this model, and align the representations. Any other questions on this?
I see that the teacher is an exponential moving average of
Yeah,
students.
yeah.
How does this differ if we learn? Is this just the standard practice? I saw it's a dyno also, so I'm wondering.
Yeah, I mean, this entire self-flow paper is meant to discourage people from using dyno. Because dyno is, again, an external model trained on external data, frozen data that has nothing to do with the data that you're training on now. And we show that it is actually better to evolve the representations as the model goes. When you're using an external model here or training an external model here, you always have this tension between, is this model really the best representation for the model that I'm now training? So this EMA thing, you can actually not use the EMA, but just use the copy of the student, and it performs really nice as well. But the idea is that the model needs to develop its own representations that are ideal for its own task, which is the generative task, right? Interestingly, I don't show this here, but we found that, for example, for video, most of the models that we aligned with, VJEPA, Segment Anything 3, all of them made it worse, significantly worse than just the baseline model. So there is something about external alignment that is just unpredictable. Is this bias that I'm taking for another model good for this model that I'm now working with? Is it contradicting what this model is supposed to learn? So when you're using external representations, it's always a wild card. It can be good, it can be terribly bad. This is why we kind of wanted the model to develop its own notion of representations. Any other questions on this? Okay. So as I said, REPA did experiments on ImageNet because it's a university paper and they had limited resources, but this is a paper from Black Forest Lab, so we had the luxury of more resources. And then I did this experiment for text-to-image, text-to-video, and text-to-audio compared to REPA. So the dashed line here is vanilla flow matching without any representation learning. The blue lines are REPA, and the orange lines are ours. So you can see that when we deviate from ImageNet and go to real use cases, it is pretty much strictly always better for the model to learn its own strong representations rather than borrowing it from an external model. Not only do we converge faster, but you can also see that purposefully I trained this until the point where REPA was kind of struggling to improve anymore, and ours continues to improve, okay? So this is a nice indication of, in REPA, the magic component wasn't Dino. It was the fact that this model was screaming and begging for an objective that is not just pixel bound, but something that is a bit harder and more complicated and more representation bound. The most important thing for us is scaling laws, because this is the motivation that started this entire thing, right? We want scaling laws to work. We need scaling laws to work. This is the basis of these entire foundation models that are now working really nicely. So what happens is we scale the model, and here the question is also very interesting, because when we use REPA, we have this external model that is always the tiniest model, right? We said the Dino V2B paradox, the Dino V2B curse. This is just 86 million parameters. So as we scale the model, this teacher gets negligible in terms of the amount of compute we pay for the teacher. Whereas with self-flow, we do an additional forward pass through a teacher, which is the same size as the student. So we're paying twice the compute for the forward pass. Okay, not twice the compute for the backward pass, because the backward only goes through the student, but we are paying a significantly higher price. So we can think that maybe these nice results that we saw are just because we're investing more compute in this problem. So a good question is, what happens when we measure the training flops versus the performance of a text-to-image model, the CLIP score? Okay, so you can see here different scales of the model. The blue is depth 8, which is, I think, 300 million parameters. And the red is the largest, is a 1 billion parameter model with depth 28. And you can see that actually the gap between self-flow and REPA widens as the model gets bigger. So as the model gets bigger, we don't just pay more for the compute, we actually get more returns. So for the same amount of flops with self-flow, which is the circles, you get more gains than you do with REPA. To the point where if you look at REPA at 28 depth, that's the red triangles, and self-flow with depth 21, which is almost half the parameters, right? The green circle. You can see that the green circle outperforms the red triangle, meaning self-flow beats REPA with twice the parameters when you scale this enough, because the model is able to learn a representation space that is more optimal for its task. Okay? So this is a pretty impressive result. Questions on scaling laws? Okay. So since we don't need one other limitation of using external representations, is that you need a representation learner for this specific task, right? So for image, I need an image teacher. For video, I need a video teacher. For audio, I need an audio teacher. But here, the model teaches itself as it goes. So I can train a single model on multiple modalities jointly. So I can train a model to generate images, videos, and audio simultaneously. And what we do is we just create different linear projection layers in the input and in the output, depending on the modality. And what you can see here is that no matter which modality we scale, so here, for example, in the losses, you know, W image plus W video plus W audio, these scale each one of the losses. And then we try different scales where in some cases we highlight the image, in some cases we highlight the video, and in some cases we highlight the audio. And we tried all these different variations of how to scale each one of the losses. And we found that no matter how much you choose to scale each one of them, so do I put more emphasis on image, on video, or on audio? In all cases, self-flow was better than flow matching. Okay, so you can see here the area between the triangles is the improvement for the different weightings, or the different ways to set the weights for each one of the modalities. So even when I weight image very, very heavily, which is this end here, close to the image FID, you can see that the video FVD and the audio FAD improve as well. So the model is able to create a representation space that is simultaneously better for multiple modalities at the same time. This is not a trivial task, because audio and image and video are very different from each other. So it's not clear that we can find a method that optimizes something that is best or better for all of them simultaneously. And one of the interesting bits about this work is that unlike Attend and Excite and unlike Video Jam, in both of these previous works, we had a very clear end goal in mind, right? Attend and Excite, conjunctions. Video Jam, motion. Here we're just training the model to be a better representation learner. And one question could be, what are we expecting the gains to actually be in our final model? And these are results from our multi-model model that I just talked about. So image, video, and audio jointly in a single model. One of the things that popped out most, which is a huge use case for companies, is text rendering. So you can see the difference between using flow matching and using self-flow for the same number of steps. The model is able to spell much nicer, which maybe correlates with the global representations that we talked about or the global properties that we talked about. So I tried a lot of different variations for this. So maybe if I don't do this with a nice neon sign, but with handwritten text on a mirror, this worked too. With longer text, this is a relatively small model in industry standards. So small model, big dream, so it's better also at spelling. Black Forest Street. So I tried all these variations of different types of text that I could think about, and across all of them, the improvement was very overwhelming. So this means that we didn't just fix, a targeted use case, but actually something that is a very wide phenomenon. When you look at the videos, this was a bit sad, but also a bit happy, because in Video Jam, I did an entire paper just on this, right? An entire method just to do this. And this is just a nice side effect of self-flow. So better structure, better motion, more coherent physics is something that was very obvious in this model. And you can see that the generations aren't that different, right? It's the same model trained on the same data for the same amount of steps. So you can really see nice comparison side by side. Any questions on this before we move to the last bit? OK. So the last bit is actually an open question. We started exploring this, but I don't feel like we scratched the surface even on this. So the question is, we showed now one direction. We showed that good representations help good generation. But the question is, does the other way around also apply? Meaning, if we have a strong model that is both generative and representation, is it also a better representation learner than a representation learner trained with just the representation objective, say masked autoencoding? Okay, so this is an open problem, but we started to try to understand whether or not the representations are actually better in this. So let's look at a downstream task that is also very interesting today to a lot of people, which is robotics, okay? What we're now trying to do is we're trying to understand if the representations are stronger in our new model than in our previous model. So what we did is we took our multi-model model that we just saw, and we fine-tuned it on basically not just videos, but also projections of robotics actions. So what we did is, in addition to predicting the video, you also predict a 7D action prediction vector. So 3 dimensions for the location, 3 dimensions for the rotation, and 1 dimension for whether the grip is closed or open. And we fine-tuned it on 73.5K episodes, okay, of different actions. This is just to see if just the generations are better, or is this a better downstream task learner for tasks like robotics? And you can see the comparison between a model starting from flow matching, the orange one, and the model starting from self-flow. So when we converge both of these models, they don't improve much more. You can see about a 20% success rate difference between a flow matching-based model and a self-flow-based model, meaning the self-flow-based model was actually better at the downstream task of predicting actions, which is really cool, because now we can see that those representations are useful not just for the generative cause, but actually to use this model as a downstream task learner. Also, when you break this down into actions, okay, I won't get into all the actions that you're seeing here, but what we saw is that when we scale this and get this to saturate, the actions that improve most are actually the more complicated actions. So self-flow was much better than flow matching, specifically for the actions that are very challenging, the ones that only get to 50% maximum success rate. Let's take a look at what this looks like. This is flow matching. It's supposed to take, right? It's a simulation. So we take our 7 predicted actions and just simulate them on the robotic arm. So the robotic arm is supposed to take the can and bring it near. So this is flow matching, and this is self-flow. And here it's supposed to close the drawer. This is flow matching, and this is self-flow. So it looks like we didn't only create a model that is better at generating things, it's also better at downstream tasks. So these representations are more robust, just stronger. We still haven't answered the question whether or not this is a better representation learner in general. Meaning, if we take this self-flow approach and scale it to the maximum, okay, is it better than Dino V3? Is it better than VJEPA? Is it better than all these models that were trained just specifically to do representations? There is one intuition to suggest that this could be better, which is just the sheer scaling of things. So if you saw the latest Dino paper, they were actually able to scale Dino to 7B parameters. Okay, so it's harder to scale representation learners because they tend to mode collapse. However, generative models scale very naturally and very easily. We can get to 7B, 10B, 80B without even blinking because this doesn't collapse. So just by sheer ability to scale this really easily, we can hypothesize that this will be a better representation learner by its sheer ability to scale than Dino. But we still don't know and are still not sure if the direction of generative models is really helpful, or this localized understanding, high-frequency understanding, is also important for representation learning, which is an open question. We haven't been able to answer it with the scope of this paper, but I think it's really fascinating to continue to consider. Another question is unification the best path forward, right? You have a lot of really famous scientists. I think Jan LeCun had a paper, a position paper at ICML saying that it's better not to consolidate, but to have different models. One is a representation learner, one is a generative model. Maybe we just haven't found the right way of combining both. So what is the right approach to create really strong models? Is it unification? Or is it each model does its task really, really well, and then we think about some method of combining them? So a lot of open questions on this. Yeah, that's the open question that we talked about now, but I'm done. This is what we've gotten to so far, and I hope you enjoyed, and I'm happy to answer any questions you have at this point.
Thanks a lot. Very interesting. Okay. Yeah, plenty of questions.
Did you observe anything that got worse with your setup? So, like you showed, like physics were better to like fuse these objectives, but is there something that just breaks more likely than just
Interestingly, no. I kind of thought that when we just did the DTS thing and just without a representation objective, just played around with the time steps during training, it would be much worse. Because we're doing this train-inference mismatch, it still does see some unified noises, but with a much lower probability. And even in that case, results improved. So really across the board, I don't like to say this because it does have limitations. Again, the main limitation is you need to do 2 forward passes. So the question is, how do you mitigate those 2 forward passes? Or more interestingly, can we create a single objective that is good for both of them simultaneously? So what we claimed here was that the noising is not good for representation, so we had to add an additional objective, but can we find a single objective that encourages the model to learn both simultaneously without having to go through this additional forward pass? So there are limitations. However, we've always seen gain from applying this.
Yeah. First of all, thanks for the nice talk and overview, and very appreciated. Thank you so much.
Yeah, thank you.
My question is on overall data size, and I'm happy to take a question. My question is on overall data sizes and model scalings, as you showed. Internet is full of data, and we can nicely scale across that data, but our life is so much, heavy-taily that we have many applications with very limited data. And my question would be, how do you think we can translate all the nice findings from you to those applications where you have, by far, not millions of videos, not even hundreds of thousands?
Yeah, so I guess the premise of this talk, I kind of had chats with some people about this earlier. The premise of this talk is that data is not a bottleneck, because the premise was that we have enough data to just learn this information from the data. But I do feel like if you have a more robust learner that has stronger representations, in theory, it should be able to adapt to those tails better, because it's in some sense less overfitted to the specific properties of the data that it saw. So it would be very interesting to do the same comparison that we did for robotics for cases such as the ones that you're describing. To some extent, it is a similar case because it's a new task and we didn't do this on a lot of data purposefully because we didn't actually have infinite compute for this research paper. So I think this is a good simulation of actually the question that you're asking, but it would be interesting to do a wider study.
Thanks.
Also, thank you for the talk. Maybe a little bit connected to the last question. Do you see any opportunities in the direction of like synthetic data for larger scale pre-training? There are these TAP, PFN, prior fitted network models that do like, basically synthetic data to then learn the overall distribution. And is this maybe a step also forward to then solve like this heavy-tailed problems?
Yeah, I can see how, again, since you're less overfitted to the actual high frequencies of the data, this could make better use of synthetic data. I personally am not the biggest fan of synthetic data and have not used it personally, but I can see how you would say, okay, I have the synthetic data for this task where I don't have a lot of real data for. I will train this with this thing where it's not really, tied to the bits and the bytes and the high frequencies of the information, and then we'll be able to adapt it more easily to my real distribution because it's less overfitted. So
thank you.
Sorry, you have to ask for questions.
One more question, if I may. I was wondering when you had all of the MAE examples also on the slide, what happens in cases where you have objects that are built extremely hierarchical and where you have in the smallest hierarchy a part of your object which is so small that it's completely hidden within one masked patch, and it's kind of impossible to derive this specific feature from all the non-masked patches. What can you do still in these scenarios? Biology is in that case, defects in stuff is in that way, so you have many applications with super different scales.
Yeah, so again, the hypothesis of this work was that we have enough data. So at larger scales of data, you would see even this, if you have this tiny object, you would see some images that are zoomed in on it and some images that are zoomed out on it. But you can always play with the granularity. So we talked about the masking ratio, how many tokens are assigned each time step, which is one way, one lever to play with this. But you also have the resolution of the tokenization of the thing, right? So the more tiny tokenization you have, the more you are sensitive to each pixel in the actual image. So I guess when you have this case where the data contains something that is super tiny in this large image, you would want a tokenization method that could be more granular or more fine-grained on some regions of the image, and then less granular on some other parts of the image, but it depends on how you define your tokenization and your task.
Could you imagine of making such a hierarchical masking directly during training that you first,
I actually, one interesting bit is that since I was so worried about, related to the question that you asked about when this doesn't work, I was really sure that this wouldn't work in the DTS case, just DTS without the additional representation task. So I tried a lot of variations where some of the batches are with DTS, whereas other batches are completely regular diffusion. So interestingly, all the hierarchical attempts that I've made were always subpar to this DTS setup where always some information is more noise than the other information. So it's counterintuitive, but it looks like this tougher objective is helpful. So I haven't been able to get these hierarchies to work. However, this again was the case that you had enough data to basically understand the distribution from the data. And this feels like an inductive bias to me, where inductive biases are usually helpful where you don't have a lot of data or you don't have a lot of scale, and then you need to help the model gain this bias that would help it solve the problem easier, right?
Thanks.
Any other questions?
So
So your model outperforms the other ones.
Yes.
But what about interpretability of the model, the new one, where you mix representation and image-based guidance?
Yeah, I would assume it's an unbased assumption. That if we created a heat map for this model, it should be nicer than a heat map for the previous model, because the previous model tends to focus on spurious correlations sometimes and spurious cues. And no, but we haven't tried it. No. An interesting angle to try in the future.
Thanks a lot for the talk. I mean, in causal representation learning, usually there are several algorithms that works on reweighting and resampling, or even adding some noise to force the optimization process to converge better. Do you see that there is some connection between the noise we are adding in your framework and the same direction of work for causal?
Yeah, I would absolutely say that I would categorize this as a regularization loss, because if you look at the theoretical guarantees of flow matching, if you had infinite compute, you had infinite data, flow matching should give you an optimal solution. But we're not living in an optimal world with, so this regularization kind of helps steer the model in a healthier direction. But as I said, something that is really fascinating to me is, can we build a single objective that does both of them or encourages both of them simultaneously, which is something that I haven't been able to come up with yet. It's always been this trade-off. You either focus on high frequencies or you focus on low frequencies. So I can definitely see this as a regularization term, but it would be really neat if we had just a single objective that does both of them.
Thanks.